can move the deadline. I don't want to like open Grayscope right now. I mean, we can, but just give me a sec. This is running. What do we have? Let me quickly. I'll start sharing and I will take a look at Grayscope to fix the date. Okay, this I assume is shared. So you're saying that on Grayscope I somehow messed up the date and didn't
like the notice was posted in Canvas, and it had a link to the Grayscope. When you click on the link, and it wouldn't open the site.
Yeah, let me take a look. What am I doing here? No, that's quite possible. So edit outline. Settings. Yeah, posted only. What? When? 23rd. Yeah, sorry. That was lame. So okay, I'll move the date to tomorrow to make sure that everyone has time. Thank you for mentioning. Okay. So hopefully this is not recorded, although it might be. Who knows? Okay, sure. Okay, so back to the lecture. So let's quickly recap where we are. So last week we were looking at how we implement system calls. We finished interrupts, and now we understand how the system gets into the kernel. Let me quickly remind you. So kind of this diagram, meaning that like either you're preempted with an asynchronous interrupt like a timer, or your user code invokes int64. Let me just quickly connect this thing. What is it? Bluetooth is off. How would that be? Okay, this is connected. So either you like preempt it or you invoke int64 doing a syscall. We like during the system call transition, everything follows the interrupt rules because you just invoke this interrupt 64, and it works because we marked interrupt 64 as invocable from privilege level 3. That's why this instruction goes through without like causing a protection violation. Like the hardware itself says, okay, look, I'm gonna look at the interrupt descriptor table. We'll pick up two things from there. So one is the address of the handler itself, which will lead us to this a short sequence of assembly instructions, which we auto-generated from running like Perl script, and the label is called vector64, which is spelled correctly. And the second thing is the code segment, which allows us to pick up the new entry in a global descriptor table. And this allows us to switch from privilege level 3 to privilege level 0, meaning we now run in privilege mode and can invoke all the instructions like reload the page table and stuff like that in order to make sure that this transition is secure. The hardware says, okay, look, I don't really know the value. I cannot trust the value of RSP because the user can change it to some like whatever obscure value, for example, pointing to an unmapped page. The hardware says, okay, I'm gonna pick up the new stack. And the way the hardware does it is that it says, look, I have another register which stores the task state segment, and it's an entry in a global descriptor table which points to yet another data structure, which is called TSS, or task states segment. And this data structure TSS will have a pointer to the new kernel stack. And hardware does it, and it also like loads the stack segment with the value of SS, which is here in TSS as well. And at this point, the hardware has this new kernel stack, and it pushes this regular 5 things on a stack, and some additional interrupts would push an error code here. But at this point, we're running in the kernel, right? And this is the system call. And we talked about it, like then we go through the kernel, vector 64, sorry, with like then all traps. All traps save all the registers. All traps then go to a trap function, which is the first C function, which we invoke. And the trap function, if we saved all the registers on this on this stack, like RIX, RBX, and so on, this all traps takes a pointer to this data structure, to this stack essentially, which is it called the struct trap frame, right? And at this point, we can access all the saved user registers if we need. We also push like syscall number here, or whatever, int number here on a stack, so we know which interrupt was invoked, right? And at this point, we stopped, and I said, okay, the only last thing which we have to figure out is how user code passes arguments into the system calls. So for example, if you have something like a write system call, which takes 3 arguments, file descriptor, pointer to a buffer, and a length on the buffer. File descriptor is just a number, so it's an integer. Buffer is a pointer, which will be pointing somewhere in the user memory here, and the length is another integer, which controls the length of this buffer. How do we pass these 3? And this is where we stopped last time on Thursday. So question?
Yeah, so how does the kernel differentiate between the different systems?
How does the kernel...
Print that for something.
Okay, so yeah. Okay, do we remember this? Does anyone remember how we differentiate? So for example, if the kernel invokes int64, but it means to invoke fork or means to invoke write, how do we do this? Correct. So like in the real life, it's if you're designing a new operating system kernel, you can choose like this convention is not set in stone. You can do whatever you want. And it like you can either push this number on a stack, or it kind of makes sense to push it in a register, right? And so what most kernels do, it says, okay, look, each system call will be assigned a number, and this number will be placed in the RIX register, right? But it's only for the syscall, because right before invoking the syscall here with this int64 instruction, you will push this value into the register, right? And let me show you real quick how it's done. This was on my very first slide. This is how it was done. So if this is the system call invocation, eventually this is int64 instruction. Right before that, you say, look, the number which corresponds to the exec, I'll push it in the RIX register. Make sense? Okay. Any other questions about the syscalls before we move forward? I forgot which slide I was using for drawings. Wait, this one. All good? So what about system call arguments? The system call arguments will follow the same convention. However, the kernel itself has to carefully check whether the arguments are correct, right? And so, for example, this is an implementation of a syswrite system call, right? Which, as I said, takes the 3 arguments, file descriptor, buffer, pointer to a buffer, and a number. And we talked about it, that system calls are implemented as an array of void functions. So essentially, a void function itself doesn't take an argument. But what happens here is that in each system call in a kernel, you will be carefully fetching each of those arguments, right? And this is done for, first of all, like the calling convention is slightly different, right? Like the stack of the system call is slightly different. The way you push the arguments is slightly different, right? All the similar, because the first argument will be still the same RSI or whatever the registers we're typically using, right? But in order to essentially access any of those numbers, you have to carefully check that they actually point to valid locations in the user address space, instead of, for example, pointing like buffer can point to location of a, for example, PML4 in the kernel, which is obviously an attack. If you say, no, with the write, it's not an attack, but if you do a read system call and read something from disk in the page table, that essentially just allows you to overwrite the page table, right? So, okay, sure. So how we do this? So kernel provides a collection of those functions, right? And on each system call, you invoke these functions to check whether, like, to fetch a specific argument of a specific type. So for example, to fetch an integer, you say, sure, please give me an integer argument from a user address space. And you take a couple of things here. You take a system call, you take an argument number, and you will return a pointer to this integer, right? And so specifically what's going on here is that it uses a helper function, which says, okay, fetch me a 64-bit number from which might be passed as an argument to a system call. And you say, why are we doing this? We're doing this because the first 6 arguments will be passed in registers. And that's kind of convenient because, okay, this is the calling convention. This allows you to in the user code, you can create a wrapper which just says write one buff n, for example, and the compiler to generate this calling convention, to generate this call site invocation. For example, when you call something like a write label, the compiler itself will correctly push, it will move 1 into the RDI register. We'll move the buffer into the RSI register and so on, right? So you don't have to do anything, no custom code generated. It's all just handled by the compiler because this calling convention matches the calling convention of a system 5, right? Like the system convention which we used all along in this class. However, of course, in order to fetch those arguments, you have to access them from the trap frame data structure because this is where they are, right? So they are not sitting in the registers. They were really pushed by the all trap function on the stack. So essentially, if we go back here, this is where RSI will be sitting. Make sense? And so essentially, when we were executing in user, RSI was actually, the value of RSI was a hardware register, was sitting on the CPU, right? As part of this transition, we went through the interrupt descriptor table, and the hardware didn't do anything with RSI. It's still the value sits in register. But as part, when we landed on vector 64, then went into the all trap function, the part of this all trap function pushed the current value of RSI on the stack, right? And the stack itself is passed inside the trap function as a trap frame data structure. That's why inside traps, you can access it as trap frame RSI, for example. Make sense? And this is the user value of RSI. Any questions? Okay. Sure. How will we access the system call argument number 7? Where is it now? Let me actually erase everything on this slide to make it a little cleaner. So I will redraw here, error code, syscall number, or, well, interrupt number. All the registers like RAX, RBX, and so on top of this stack, right? RB, whatever, 15, right? R15. Sure. So where is the syscall argument number 7? Or is it? Who can find it on this picture? Beyond the exam, find argument number 8.
RSP that was saved by hardware, would it be on that stack?
RSP will be here, correct. User as RSP is here, that's true. But where is the argument 7? Will it be? What's the calling convention? So for example, when you invoke a write system call, no, write doesn't take 7 arguments. I don't think there is a 7 any of the system calls in x6 takes 7 arguments, but just for the sake of example, imagine, right, like one of them. Let me just erase everything. Erase right here. And imagine we have like foobar. And it takes arg0, arg1, and so on up until arg, what is it? 7. It's 8, right? So then arg6, right? This goes like when you generate the call site invocation for this one, right? So like just for the sake of example, call foobar. You will move arg1 or like arg0 into what is it, RSI. You will move, the compiler will generate this code arg1 into what is it, RDI, and so on. And what will happen to argument number 6? Where will it be? What will it will be pushed on the stack, the user stack. I agree. So it will be something like whatever. Just a sec. So it will be something like, instead of a register here, it will be something like RSP plus some delta, right? Or maybe minus, right? Or alternatively, you can use a push instruction here. Agree with this? So if we understand this call site invocation, and this foobar label leads us to auto-generated something, which is something like foobar, which in the end invokes int64. Before that, it will push system call number, let's say, I don't know which number, 55, for example, into the RAX register. Make sense, right? Invoke 64. This is how we drop into the kernel. So we are looking for argument 6, right? So where is it on this diagram then? It will be on the user stack, so right? It will be somewhere, I mean, probably this specific stack layout is not correct, but it will be pushed here like as argument 6. After that, we actually invoke write, so there will be like a return value to, or return like from foobar. And this will be a value of RSP when we enter the kernel. Make sense? So our 7th argument is sitting right here on the user stack. That makes sense? So in order to fetch this argument, which location do we have to access? No, obvious.
Reference the value from trap frame, RSP value.
Correct. So trap frame, RSP plus the return address, which is 8 bytes, plus the n multiplied by 8, where n will be a system call number or argument number. Make sense? Right? Agree with this? So the first 6 arguments will be in registers. Where is it? And the other ones will be on the stack. Yep. Which one?
The one where you were.
Well, I'll show you a formula, and my formula might be incorrect. I mean, I made it up. Just a second. Yeah. Yeah, so let's take a look. That's what I was trying to show you, the formula in the code. So the formula in the code will be something like, just a sec. Keep losing this. Something like this. So essentially you say, look, for the first 6 from starting from 0, for the first 7, then I will figure out the values from registers. If, however, I'm looking for the value above, I will do +8, which is the return value. I will do this drop frame plus RSP, and then we'll fetch the value from user stack, right? However, you cannot access this value directly. Why is that? Why can't you access the value on the user stack? You say, yes, you said dereference, but we cannot dereference. What's the problem with dereferencing a value on the user stack? Do we trust user stack? Correct, because this RSP can point anywhere and we don't know whether it can be trusted. That's why we use another wrapper function, which is fetch integer. And this fetch integer is a secure function which fetches something from user memory, right? Let's take a look at how it works. Specifically, fetch int does the following checks. It takes it says a pointer to user memory as an address, and it returns the value, right? And the way it does it, in order to check whether the pointer itself belongs to the user address space, we do the following check. When we create a process, and we will do it later today, we keep tracking the size of the user memory. So, and this will be the size variable inside the proc data structure, right? And we say, look, for sure, if this address sits entirely, actually, if it's above the current size of the user space, and user can be very, very funky, and it can like pass the value which is on the edge, like the first byte, for example, within the address space, but the other bytes, the other 3 bytes will be outside. That's why we have to check address plus 8, the other 8 bytes, right? In whether they are entirely within the user address space. If its condition is true, then we return -1 saying that the user is trying to attack us. If not, it's safe to read the value because it's in the user address space, right? Make sense? It, however, makes the following assumption. It says, okay, user address space cannot have any of the holes here because we checked essentially like all the pages from 0 to size have to be mapped, right? Just remember it. We'll come back to it in a second. So it's an interesting assumption. But other than that, we kind of like, we agree on that. We say, look, we pass the addresses within the current size of the user address space, and address plus 8, because we're fetching a 64-bit argument, is also within the user address space. So it's safe to access. At this point, we access the value and we just return it, right? Make sense? And if you build a new system call, so you will have to wrap all the fetching, all the argument fetching in a similar manner, right? And of course, like you say, sure, like I kind of got it. So, but what if I'm trying to fetch a pointer, for example? Like let's imagine we fetched an integer, like argint. We looked at argint, right? And we fetch a 64-bit integer with this argint, which fetches the n value. How do we fetch a pointer? How do we fetch a buffer? What's inside this argptr function? The logic should be obviously similar, but let's try to guess how can we build it? Correct. So essentially here, we take an additional argument n, we fetched n here, and we say, look, if we want to fetch a pointer to an object from user address space, we have to provide a size of this object, and we'll check that the object is entirely contained within the user address space. Agree? So similar to an integer, but integer is a fixed size, so 8 bytes, and the buffer can be variable size. So we do the same. So we say, look, sure, it's like we first check that the pointer itself is sound, like because pointer can be passed as one of the first 6 arguments or a 7th argument on a stack. So we cannot like directly access it, right? So we fetch it similar to argint64, essentially, because if it's on a stack and user tries to fool us, sure, if it's there, then we say for sure, then fetch the object itself. So I points to an object, and we have a size passed here. So we say, well, if size is negative, go away. If size is positive, we just say that, okay, sure, this thing has to be within the address space, right? And at this point, we say, look, we checked it, and let's have this pointer is now safe to access. So it's a buffer to user memory, but we know that this memory is safe to access, right? There is a little bit of a trickery here. That's a good question for the exam.
Well, I have a question about this. If the
Yeah.
double pointer in the function signature.
Yeah.
They're just getting the first entry double pointer.
They're just assigning, it's a pointer to a pointer. It's a way to return a pointer from a function, right, in C. And so you're returning a pointer by saying, okay, I will return a pointer to a pointer. And you are assigning, you say, look, I checked that this pointer I points to somewhere within the address space. And so right now it's safe to access, right? My question, which I wanted, and I stopped for a second, is that those checks assume that the address space of a process does not change the very next moment. So what is this assumption? There's a couple of assumptions here, and this gets you to like a real hardcore or like core of the security research. I mean, you did the checks. At this point, you're returning and you're saying, look, for sure, I just checked as a system designer, I checked that my pointer, which like passed to me and I use it somewhere on a kernel heap, points to somewhere inside the user address space. But there's immediately a couple of questions, like, can this change? Can the address space, like proc size change? Can it or not? And why? So assumption number one is that x86 doesn't have threads. And I cannot write threads, but assume it's threads. What is that? And no threads, which means that there is no other threads which runs in this address space, which concurrently can deallocate part of this address space. Do you agree with this? Right? So I didn't explain threading, but if there were threads and some other system call can say, look, like deallocate this heap, for example, then it's a bug in the kernel, right? Exploitable. Agree? Okay, so that's an important assumption. So there will be a homework which asks you to build threads, maybe. And we're not going to go into these details, but obviously that's a problem if you have threads. The second assumption there is which? What is the second assumption? Well, what if the system call itself deallocates memory? Can it happen? Or not? Something like SBRK. SBRK sets it can deallocate memory by requesting shrinking the size of memory, right? Well, x86 doesn't have unmap, so the only way to do unmap is invoke as SBRK with some negative number, like whatever. And this is effectively an equivalent of unmap in x86. But on Linux, yes, unmap is a real pain, right? And here you say, look, wow. At this point, every time you add a syscall, you should say, look, I should maintain this invariant inside that the system call, if it changes the address space, at least the arguments will not be. I'm not exactly sure that this is not a bug in x86. So effectively, SBRK takes an argument. Okay, it's not a bug because this argument is in the register, right? So, and it's not touching the user memory. But for example, if if for a moment you extend x6 for SBRK, which takes 7 arguments, and the first 6 are in registers and the 7th ones is on the stack, there might be a possibility to shrink the address space to the point that it's like it deallocates the stack, which probably, again, not true in x6, but just like I'm trying to illustrate the complexity of this reasoning.
So would the second assumption then be that we might potentially change the process address space?
Right. And this example of this check is a time of check, time of use attack, meaning that it's quite common in real systems. You check something, assuming the state of the system at a point X. You do the check, and then immediately the state changes. And in many systems, it's so complicated, like ensuring atomicity of using the data after the check is very, very hard. So it's quite common attack in real kernels, real web browsers as well. Like it gets involved, but I wanted to illustrate this point. Okay, makes sense? Okay, but at least we understand the checks. We say, okay, x6 is atomic. There is not a single syscall which deallocates the address space, or at least not a single one besides SBRK. I would assume, right? But okay, not 100% sure, but kind of looks like it. And there are no threads in the kernel. That's why no one can deallocate the address space concurrently. So it looks legit. And we'll also make an assumption that the entire address space from size to 0 is mapped, right? Make sense? Okay, cool. Then we're good with this. Okay, sure. So this is how we fetch integers, pointers. This is the checks, and this is more or less the end of my syscall lecture, and I'm ready to essentially move to the next one. Do we have any questions about interrupts or system calls? And I mean, it's important to understand how they work. Why is that? Because there will be a homework assignment asking you to add a new system call into the x86 kernel. And also in general, I like to ask questions about those transitions because it's kind of like a cross-cutting concern, which I think everyone has to understand. All good? Okay, sure. So we're done with syscalls. So we kind of understand how the interrupts are delivered. System calls are not far from interrupts. So let me then quickly change this slide deck and move to the next lecture. And the next one is actually creation of processes. And let me explain how we go about it. Let me just make sure that I'm sharing it as well. What am I sharing? Desktop 2. Okay, cool. Share. Okay, so again, we learned a fair amount of what's going on in the kernel. Like we can boot into main, we can set up different bits of like infrastructure, like page tables, global descriptor table. We understand how like privilege levels work. We understand how interrupts are delivered. A couple of things which we don't understand yet, which are critical for kind of like building a very minimal kernel is, first of all, how we create a very first process, and then how we switch into this first process, and in general, how we switch between processes and start running them, right? And so today, and it will take us at least 2 lectures, we will start talking about how we create processes. And instead of explaining how we create the very first process, I will first explain how exact system call works. It's just easier this way. And then I will show how the first process is created. It's kind of similar, right? So at this point, like just imagine for a second, we already have a process running. And the first one, the second, maybe it's shell. And this process invokes exact system call, right? And we know how exact system calls are like invoked, right? So the question like, what is inside exact system call specifically? What kind of code you have to write if you build in the kernel? And in this homework number 3, you're building like a minimal kernel which sets up page tables. But imagine we're building new system calls, right? The question is, what needs to happen there? So if I ask you this question, what should be inside exec? Correct. So what you're saying is that exec is really two parts, right? And I have a slide for it. Let me just show you. It's not my next slide, but I just wanted to make sure that that we all understand that Jesus is like essentially you say, look, I will be allocating parts of the address space and I will be loading those parts from the L file from disk, right? Make sense? At a high level, it's kind of like not super hard, right? But I mean, as usual, everything is in the details, right? So let's just go step by step. So imagine, and again, you can make different choices when you build a new operating system, but in x86, the following choice is made, right? You say every process will be linked and loaded, linked to statically, no dynamic linking, no position independent code, no complexities. Everything is ready to go, just load it at address 0, right? Imagine like the compiler, you invoke GCC, and if you carefully like look through the make files, GCC does it. Make files do this, like everything is linked to run at address 0, right? It will pass this -t argument or whatever it is to say that's 0, right? Make sense? Okay, sure. And we say, look, like obviously, naturally, we load the text section, process text section, process data section, plus maybe BSS. I'm not like, and we don't know the size, but sure, we have to implement like some dynamic logic to say we read the ELF file, ELF from disk, and ELF file will, as we know, will have an ELF header. ELF header will point to other parts of the file. We will load those parts into those like addresses of memory. And as we go forward, we have to actually allocate pages for this memory, right? Because we have to construct this address space. And as we discussed before, we said, okay, it's all nice, but each process will actually have the kernel part of the address space. And that's so we can invoke like int 64 and immediately land on the like entry on the vector 64 here and start executing it without changing the page table, right? We get this argument that the page table is not changed explicitly by the hardware during the system call, so it has to map those kernel pages. Only the privilege level changes. So here we were running at privilege level 3. Here we're going to be running at privilege level 0, but that's fine. We know how to do it because, you know, the code segment which we're going to place in the IDT will lead us to the GDT entry, which will have a privilege level 0, right? So that's fine. But as long as the pages are mapped, then we are fine. We don't have to do anything, right? So we map the kernel part of the address space, right? And sure, so each process itself will have an address space which maps the user part, the kernel part of the address space, and those user parts like process text, process data. Then we say, obviously, process will need its stack. So we'll create a page for the stack. RSP will be pointing here. We'll place a little guard page here. And a guard page is kind of a soft mechanism to protect against the stack overflow. So meaning that if you're running, if you like pushing, you have some recursive function invocations here, or just allocating some stuff on the stack, at some point you might run out of the stack space. And at some point you hit the guard page, and at least you crash immediately. Not always, but in a good case, you try to touch the guard page. If the guard page is not mapped, then you get a page fault, and at least you immediately get a SAC fault instead of like trying to overwrite process data section, for example, which may lead to some very, very interesting bugs which are hard to debug, right? And I'm saying not always. Under what condition you might not crash on a guard page? Who could tell me? Like literally, guard page will be a page of 496 bytes right below the stack, which will not be mapped, or will mapped with such a flag that it will trigger a page fault.
If you put something on the stack that you
Correct. So if you suddenly write a function like foobar, and this function has a local variable, like a character array, which is like whatever, buzz, and it's the size 497, for example, or even 496, because something will already be pushed on the stack, then it puts you over the guard page, right? And then you can start actually touching the kernel data, which kind of sucks, right? So the guard, that's why I'm saying guard page is a soft mechanism. So an attacker can actually jump over the guard by adjusting the stack value, right? And you can make this mistake by suddenly saying, okay, I don't really know the size of the guard page, but I assume it's a page. So if I allocate this data structure accidentally, for example, or if you are in some adversary scenario trying to attack the code of the program. Make sense? So the guard pages don't really like protect you bulletproof from Stack Overflow attacks, but they at least like they help you to avoid the obvious cases. Okay, sure. So any questions about this? That's our goal. We say, look, for each process, we will construct the address space, which consists of two parts, which will contain the upper part of the address space and the user part of the address space. And initially, user part will be empty, but as we will be moving through the L file, we will be allocating pages and mapping them and making sure that the bits of the text section will be loaded into those new pages. And we don't know exactly, but I mean, in general, x86 itself, it's a generic kernel. It just says, well, I don't really know what kind of linkage you're using. So the process might start from somewhere here, like the data section might start at address 1 megabyte, and the x86 actually has to be correct to make sure that all the pages from 0 to 1 are mapped, just because of the security assumption, which we just use in the system call, and then start adding those pages for the text section here, right? But let's assume everything is fine and we start from address 0. Make sense? Okay, sure. So how do we do this? Yeah, so exec, a typical system call, takes a pass to the binary. Like, for example, you're already running shell, which maybe you created, a shell forked. We're not going to talk about fork for a second, but exec takes an argument, a string to the next binary, an array of argv. We'll discuss what it is, but it's array of arguments, string arguments for this ls program, right? And we say, look, sure, we really want to create this address space as we just discussed. And we said, okay, we ask a question, and you, roughly speaking, you answered it already. We say, look, the idea is that we load the program from disk, accessing the L file. We create user stack page, and then more or less we can start running. So we can pass control to the entry point of the program. So essentially, RAP will be set to the entry point. And if we know how to switch to that process later, and I will explain it next week, then we're good to go, right? Eventually this process will get scheduled and we'll start executing. Make sense?
So the PML4, is that sort of, does it have its own page table?
Correct. Yeah. Yeah, correct. And you're asking, where is the proc data structure? So the proc data structure, since the kernel itself maintains a list of processes in x86 and just an array, like, so there will be array of those processes. Like, I think specifically, I mean, I can be wrong. Maybe x86 actually allocates a proc data structure on a heap. I don't remember, but like, I believe it's an array. And it's an array in a data section of the kernel sitting somewhere here, right? This array. And inside this array, there will be a pointer to the PML4, right? And PML4, we do remember for sure that we allocated on a kernel heap. And kernel heap will live somewhere like above the kernel end symbol and up to fizz top. And of course, everything is shifted with 8 terabytes. So it's fizz top plus 8 terabytes. Make sense? So one of those pages will contain PML4. Make sense? And it's a virtual address, but we know how to convert between virtual and physical by subtracting 8 terabytes, right? Or adding 8 terabytes, so it's fine.
One PML.
Correct. So essentially, this process data structure will literally have a pointer to PML4. PML4 will have pointers to PML3. PML3 will have pointers to PML2. Like, and all of them will be sitting on this kernel heap here, right? Agree? And I will explain in a second. But yes, any other questions? Okay, sure. So, okay, as I was saying, we just saw that exec, the goal is to read process binary from disk. It takes an argument to the binary pass. When we get to file systems, we will discuss this function, which is called namei. Namei takes a string, which is a pos, splits it into like substrings and like essentially goes through a directory hierarchy. Like it starts from the root or from the current folder, goes into bin and figures ls and as a file inside the bin, and it returns a pointer to the inode. And I will explain what inodes are, but let's just think of them as files, unnamed files. And so it's namei takes a string, returns an inode. I stands for inode. And so that we will have an access to a file which contains the ls binary. This returns an inode. And then we say, look, sure, well, we're going to read this, the binary, which we assume is an elf file with the readi. Readi takes a inode pointer as an argument, so that's why it's said I. We were going to read this file, understand that it's an elf file, and similar to how you build the elf loader in your homework number 2, just load this like text section, all the loadable sections into memory. And as we're going to be reading the, like if we say, look, elf has a text section, and it has whatever, it has a data section, and maybe it will have a BSS, but BSS is not stored, but we'll just take a look at it and we say, look, we need to allocate space for it. For each of those, we will be allocating pages in the process address space because we have to load the data somewhere, right? Make sense? Okay, sure, let's take a look at the source code. So again, I skipped through like the level of dispatch, system call dispatch, which checks the arguments to exec. There will be a function in x86 which does it, but this is an actual implementation of exec. At this point, we already checked that this pos is safe to access. It points to the user address space, and this array of argv is also like is safe, right? And sure, what we do here, you say we'll take the pos, use this namei function, it will return an inode pointer, and it's all good. If it like something goes wrong, file doesn't exist, it says okay, -1, so that's an error. Right? And then we says, sure, we assume that the argument to exec should be an elf file. So the very first thing we're doing, we say, look, let's just read the elf header. And we have a local variable elf, which matches the definition of the elf header. We say, sure, use this inode pointer and starting from address 0 in the inode, which inside the file, read something into the elf data structure of the size of elf, right? Or just like read the header, very similar to how you did in homework. And then we check for the magic. So if magic matches, we believe, okay, sure, it's an elf file. Let's keep going. So let's go through the like loop of sections by section, right? And our first step, we say, look, okay, at this point, we're probably ready to start creating a new process. We say, look, let's create a new address space. Meaning that we need to create an absolutely fresh, like we're currently running, CR3 is pointing to some page table on which we invoked exec, right? CR3 points to PML4 of a current process which invoked exec. It has a full tree hierarchy. One kind of appealing option is to start changing this address space, right? Because, well, why not? We like reloading we say it's a pointer to ls. Let's just change this current page table. Why it's not a good idea? Wait. Didn't fully understand you, but I think the answer is no. Like you're running, let's assume we're running in shell. Shell invokes exec, which says, okay, please turn myself into ls. And you dropped with exec into the kernel. This shell will have its own page table here, right? All other processes will have their own page tables. We're not even talking about those. Those are like completely different, right? Maybe there is like, you just forked and this is a parent shell. And it will have a CR3, or it's not pointed, but like the proc data structure of this process will point to this hierarchy. We're not touching this right? So it's other process we don't touch. The question is like, can we touch the page table of the process which invoked exec? So that's the question.
It might be like changing pages that you're running. The code you're currently running is somewhere in the page, and if you like change the page out from underneath it, it's not gonna.
That kind of sucks, but not entirely agree with you. Like, let's say you invoked int64 passing exec as an argument. So you jumped into the kernel. So you're running in the kernel part of the address space. So if you start changing this address space part of the user part of the address space, like you cannot return, but why would you return?
Get out of the kernel.
Yeah, but if you reloaded it, like if you completely reloaded it with the ls, that will be completely new address space, which contains ls, text, and data sections and a fresh stack. What's wrong with this? Well, I agree, but we just discussed that when you do exec, instead of really returning, you will configure the trap frame and its RIP register to point to the entry function of this process, right? So it's not really, it's kind of like not a real returning, it seems like, right? But still, I argue that it's not a good idea to start changing this address space. I just want to see the answer. Make sure that you understand why. So why it's not a good idea. But you got my argument. You're in the kernel. You're not changing this address part of the address space, the kernel part of the address space. So it seems okay to start like modifying in place those pages, right? Exactly. Right. So this is the only condition which you care about. You say, look, what if like exec will not fully finish and I will need to return with an error? Then if I started like erasing this address space, it will be gone, right? And then you will not be able to return. And the conditions, you say, look, I checked that ls exists in the file system. What are the conditions why exec can fail? Well, maybe you will run out of memory, right? You say, I need to allocate pages for the page table or pages for this text and data sections, and I run out of them, right? And then if you return, there will be no address space. And this is exactly the reason why you say, look, instead of like overriding my current address space, I will be constructing a brand new one. Like I will allocate a new PML4 for the future ls and will like construct all the levels of this page table. And only when I know for sure that I'm not going to fail, I will return with the success. I will deallocate this old address space and will set this like proc, I forget exactly how they call it, but PML4, for example, pointer to point to this new address space, and then it will be loaded in the CR3 register, right? Make sense? Okay, you have to be careful with exec. So that's why we're constructing the new address space. Okay, and again, since we say, look, we need a new address space, it's always a two-step process for us. We say, look, we first construct the kernel part of the address space, and we'll construct this red part as a kernel part, this green part as a user part. If I ask you a question, how to construct the kernel part of the address space, and you know the answer at this point. Again, as a designer, you try to reuse as much code as you already written, or as you already wrote.
That function when it first started.
Yeah, we have that function. Do you remember the name of that function? Set up KVM, kernel virtual memory. And we say like, sure, yeah, we checked for the magic. We move on with constructing the new address space. We call this function set up KVM, and it will return us a fresh new PML4 root and the whole page table, which will contain this kernel part of the address space, right? So it will just simply construct it. And just to remind you what's inside this function, set up KVM, allocates a new PML4, sets it to zeros, then uses this wonderful kernel like map pages function. So it's essentially just iterates to the kernel map. Do you remember the kernel map? It has 4 entries. And so essentially just like map pages can map a consecutive chunk of memory, and a kernel map controls what these 4 chunks are. And those 4 chunks are chunk number 1 for BIOS, chunk number 2 for like read-only kernel text section and read-only data, chunk number 3 here for like writable data and the kernel heap, everything up until fizstop. And the chunk number 4 is this BIOS region, which we map at the very top of the 64-bit address space, right? And we talked about it. That's why I was saying, okay, this function is important. So literally, this kernel map has 4 entries, which I just discussed. So not a very interesting thing. We go in a loop, invoke map pages. Map pages internally goes and like map one page after another. Like remember this constructing different levels of PML of page table and mapping. Essentially, what we do here, like we map everything with a 8 terabyte shift. So essentially, physical address 0 is mapped at 8 terabyte, which is defined in our kernel as a kernel base, as a macro definition. Make sense? Okay, sure. So if we invoke this function, we get a new fresh page table. It doesn't have much, just the kernel part, but it really did allocate like pages for the page table. Everything was done, so everything is running. So, but no user part whatsoever, right? Any questions about it? Okay, so that's reasonably easy. I agree with this. And now the more interesting part. So we need to start creating the user part of the address space, more specifically this part. And the way we do it is that we're going to be reading stuff from disk, understanding where it should go, and essentially loading it there, right? So at a high level, what we do here is that we go through the ELF file. We say, look, ELF wants to be loaded, like the very first like address used by the ELF. Let's say it's a text section of a program, goes at address 0. So we allocate a page, we map it, making sure that, okay, address 0 is mapped to this page. And then we just read the data from the inode into that memory. And we iterate until we reach the end of the ELF file, right? So roughly speaking, it looks like this, right? So you have something ELF sitting on disk, and you're allocating those pages, mapping them in this page table, and reading the stuff directly into those pages, right? Let's take a look how it's worked, how it's done. So again, we start with this. This is the variable which we discussed earlier today. The size of the address space originally is 0. We're going to go in a loop, like iterating the ELF program header table. Do you remember what it is? Remember ELF header. ELF header will have a pointer to the program header table, exactly your homework number 2. Program header table will have some number of entries, loadable entries. Typically, those are merged together. Something like text and read-only data will be merged. Maybe the data will be a separate section. Maybe it's all will be merged in one. And we're essentially just loading it into these addresses, right? So like there will be a virtual address, which it points to. And like essentially what we're doing here, we say, sure, like if we have a pointer where this entry is contained, just use the same inode, read it into the program header entry, and hopefully, everything goes correctly. So we're not gonna go into an error. We have the entry which we have to load into an ELF file, right? Like we read it them one by one, we go in this loop, and we're essentially incrementing this offset in the file, which we use here by the size of the program header entry, right? Makes sense? Okay, we're reading them. We say, look, sure, since we don't have memory, like, and it's similar, like in your homework number 3, you did this mmap to allocate space for the ELF, which you're loading, right? Here, we use this function, which says, okay, allocate user virtual memory. We pass a page table as an argument. We pass a size, and we pass the virtual address of the header plus the size, right? So essentially, we extending the address space from size and we started from 0. And this function is very careful. So it's designed to make sure that we're not going to skip a single page. So essentially, if this virtual address, for example, is 1 megabyte, apologies for this, and like plus whatever, plus 8 kilobytes, for example, the size. If we linked and loaded a process to run at first megabyte, it will still allocate all the pages from 0 to this new size, right? But this guarantees that we will not later fail when we invoke a system call, right? And we get the new size here as a result. Okay, let's take a look at this alloc UVM function. So again, I'm just discussing here in my slides the size variable and how it's running, essentially size of the address space. Okay, high level overview first. So if you allocated those pages and you know that alloc UVM already allocated and mapped those pages, at this point, you can use the second function, load UVM, which essentially will just take the same page table, take the virtual address of where the specific segment has to be loaded, and you say, look, this is the offset of the segment, and this is the size, so please load it at this address. And we know that this address is already mapped in this page table, right? And essentially what happens here, so alloc UVM allocates those pages, and the load UVM essentially loads those pages from disk into the memory, right? Make sense? So let's quickly go through alloc UVM just to understand how it works. So what do you think has to happen here in this alloc UVM? How to write this function? Correct. So we say, look, we have a kernel allocator, kalloc. It will return us a page. Now we have to map it into the page table. How do we do this? Imagine we want to map this page at address 0. So what function can we use? Why not to use again map pages? Like we were just looking at it. So, but I assume that if we use map pages, you say, look, you can write your own, but most likely you can reuse it. Let's take a look if it's doable, right? So you say, look, first of all, we check if this new size of the address space doesn't spill into the kernel. So that's another check. So this is 8 terabyte in our case. So everything below the 8 terabyte is fine. But if it's above, then sure, it's probably not a good idea. But what you're doing here is, let's say you're sure, like I have this round up the old size to the next page, and essentially say we'll treat it as a region, and we will use map pages internally. But what we have here, we allocate, like we're running a loop from A, which we got here, to the new size. We allocate pages one by one from the kernel memory allocator, like you said. We set them to 0, right? Just because we say, look, sure. Jesus, okay, let's skip it today. Although it's not a bad idea. Yeah, sure. Let's do a poll. So I have a poll which says, okay, sure, like, let me just patch a slide for you guys real quick. But the idea here is that, where is this memory coming from? Let me quickly do this. Okay. Otherwise, so okay, poll. Just quickly do it. Okay, free response question. Where is this memory coming from? Okay, Alec. Say again. Well, good question. What does it mean? So, I agree with you. So, what does it really mean? So, let me change it. From which memory of, from which region of DRAM and which allocator? Does it make sense? Did it change for you? Probably. And we will we'll have to grade this poll, but we'll grade it. If you say something, the kernel, be more concrete, otherwise you'll get a partial credit. And let me quickly, oops, it's connected. Am I allowed changes? Yeah. So just if you say free list, also make sure that you explain which free list. Just treat it as an exam question and just give it a second to think about and give them a better human readable answer. If you say heap, explain which heap. And just to help you a little, let me just. If I try to find this, where is this memory? Where is this page? Where will be, like you say, I forget exactly what the pointer name is with mem. If I ask you a question, if mem is pointing somewhere on this diagram, where will it point? Wait, a little louder. To where? To above the and symbol, right? Exactly here, right? So, and if I, on the exam, if I say like, give me a range for those addresses, the range will be something like kernel and to 8, not GB, 8 GB plus fistop, right? So this range. So specifically, we're managing this list of memory, right? So in physical memory, it sits above the kernel and here, and it's like it's a list of 3 pages, right? And we allocating, so we have a pointer here to the next available page, and then these pages are connected with a list, right? And we're allocating one of them from this list. Does it make sense? So it shows up in virtual memory, it shows up in this region. In physical memory, it's right here, right? And we're getting one of those pages. And you can call it a kernel heap, and I will agree with this, but I want a more specific description. And to be absolutely clear about it, this is our kernel memory allocator, which we're using, right? So it sits in the kernel, it has this virtual pointer, right, which connects the list, and then the elements of the list sitting above, right above the and symbol. Make sense? So this is where we're getting the memory from. Anyone needs more time to answer it? Yeah, for sure. Okay, this is clear.
Just curious, why is it 1 gigabyte specific?
Great question. Why is it 1 gigabyte? Do we remember why? Anyone who can answer immediately gets like A in this class.
This was defined, like, in that function, it says if this top is greater than 1 gig. or
Yeah.
only goes up to 2 gig.
It only goes up to a gig. So why is that? So fistop is somewhere here, but the kernel doesn't allow it to go above, or does it?
Well, it has that question, that ternary operator where it says if this top is like whatever, if it's bigger than.
Yeah, so why is that? No, not exactly. There was a reason for why we stopped at 1 gig, at least at the very beginning.
Page table, the assembly page map is only 1 gig.
The assembly page map, the assembly page table.
Yeah.
Correct, and that's the answer. So just to make sure that we all understand it, when we started booting on the kernel, right, and we're still in main function, we said, okay, we use this boot time page table, and it's kind of a chicken and egg problem. We say, look, we want to use large pages, and this entry only can map the region of 1 gigabyte. So at this point, we have this region mapped up to 1 gigabyte, and this region mapped from 8, is it terabytes or gigabytes? I forgot already. Let's say GB, to 8 GB plus 1 gigabyte, right? And this is just a simplification. Later on, we can map more memory, but we're still, when we initialize the memory allocator, we said, okay, look, just for simplicity, don't go beyond, because this page will not be mapped and you will not be able to write a pointer to connect it on the list. You will page fault, right? So that's why we're still on all these diagrams. And later on, at the very end of I think we can actually extend it and say, look, like we can go beyond 1 gigabyte, but we haven't reached that point yet. Okay, so this is clear. So let me stop the poll, deactivate for now. So specifically this page, which we get here, right, will be one of those pages which we got from this list, which is sitting in this region right about the end of the kernel, right? Okay, sure, but how do we map it? Like, what does it mean to map this? We say, look, sure, we can use the map pages function, and we say, look, we have a page. We will convert it back to physical address by shifting it. So this becomes a physical. And we will map just a tiny region of 1 page. So essentially, we say page size into this virtual address. And internally, map pages function will take this physical address, split it into like 9, 9, 9, and 9 bits, plus whatever, 12 bits here. We'll use it as an index into the PML4, right? We'll use this as an index into PML3. And if suddenly PML3 was not allocated, it will allocate it from the same allocator, right? So it will use kalloc internally, and so on and so on. And essentially it will map it into the address, into the virtual address A. And by the way, like what's important here, that we are not using the currently active page table, which is used by the hardware. We explicitly use a different page table, the new one, the one which we allocated just here, page dir. And we got it from kalloc as well. And this page is essentially passed here as the root of this page table, PML4. So we're not, this function map pages is written in such a manner that it doesn't change the current page table. It can change any page table, but whichever you pass, right? And we're passing a different one, right? To make sure that it's not changed. Make sense? Okay, so we use map pages, we map this page, and as you said previously, we're passing the user accessible bit here, right? Saying that it's writable page and user accessible. And sure, like it was like page table, virtual address, size of the region is 1 page, virtual to physical, stuff like that, user accessible flag. Map page is just a quick reminder, just 1 more minute. It does exactly this thing which we just discussed, right? So this is what I have it on my slide. It essentially walks through the levels. At the end, the goal is to write this physical address into the entry of PML1, but if one of those intermediate levels is not allocated, map pages will allocate those. And essentially what we're doing here, map page internally walks the page table directory for this address, gets the page table entry. That's somewhat similar to what you're doing in a homework. Like does this logic for whether it was allocated or not. And we use like multiple level walkers and stuff like that, right? So at some point, after we did the mapping, since we're going in the loop, because the text section of a program might contain multiple pages, we increment the iterator by 1 and go forward again, allocate the next page, map it again here, and so on until we map all the user memory, all the memory used for example, for this loadable section, right? Okay, sure, let's stop here. And then next time I'll finish how we load this memory from file, and then how we create the very first process.